Welcome to the pre-recording of Lecture 10 of MCS 481 on computational geometry. So we are in the fourth week of classes, but in some sense this lecture is very much self-contained. In a way, we are a little bit rebooting the course. We started with looking at polygons as the convex hulls of a finite set of points. Um, we are revisiting this problem, but we are revisiting it from the dual representation of a polygon. We can represent a polygon as the intersection of a finite number of half planes. And this leads to the topic of this lecture, linear programming. So linear programming is an extremely important algorithm. Um, in this course, we look at the geometry, and it's also a study of algorithms. We will derive an incremental algorithm, which will have a rather disappointing cost. It will be quadratic in the number of constraints. In the next lecture, we will see how with randomization we can get a better algorithm. Okay, but let's now look into what we're going to consider. Um, let's look at a computational start. So here is a picture. Actually, there are two pictures, or if you like, three pictures. At the left, we see the convex hull of 10 random points. And superimposed through the edges are the lines that are passed through those edges. So there are 10 points, and you can see that there are 6 lines, and the lines can be represented by a vector and an offset. So the picture of the right is showing all the outward pointing normals to the edges. And this can be done with numpy, scipy, and matplotlib. So to give this a little bit a more computational flavor. So here you see the code that generates pictures such as this. So I ran this on another example. So this is another random example. So this is cell 18 of the Jupyter notebook. In a way, we started in the first lecture by looking at the output of the convex hull of scipy, which wraps Q hull. In some sense, this notebook is extension of where we started in the first lecture. So this is the final result of making pictures like this. So let me now scroll up. How did I get to this? Well, we are generating. So here you see first the packages that we are using. This is a Jupyter notebook with a Python kernel with the packages numpy, scipy, and matplotlib installed. Scipy wraps the Q-hull algorithm. So the Q-hull algorithm is a very important algorithm or a very important software package in computational geometry. It does much more than just doing the convex hull. We will later see that it will also do Delaunay triangulations. But for this lecture, we import the convex hull in the plane, so not in 3 dimensions. Despite the spatial, it can do this as well. For plotting, so in some sense this is a geometry course, and I felt that there should be some plotting. This is lecture 10 already. I might have presented this earlier. But I take here 10 random points. The random points are generated by NumPy's random method, so they are all the coordinates lie in the first quadrant, so between 0 and 1. Here you see the 10 random coordinates stored in a 10 by 2 matrix. Then we compute the convex hull, and here you see what this looks like for this random example. So that is where we got it at lecture 1. So this is the view of polygons as spanned by a finite set of points. Fine. So there is the equations attribute of a hull. So hull is what was computed by this convex hull method. So we can interpret this. So if I scroll up again, so we see that there are 10 points, so these blue dots, but there are 1, 2, 3, 4, 5 edges. And the edges are, you can see them as line segments. We see them as line segments, but we can extend those line segments, and this is what these equations are. So we have three numbers. The first two numbers are the components of the vector, and the last number represents the offset. So let's visualize this. So I select the A, B, C, the three numbers from the equations output, and then I had to look to the documentation of QHull, first had it wrong. So we have the constraints which are less than. So it will turn out that this is convenient for the outward normals. Now, how do we draw a line in matplotlib? Well, we see it as a function. So I'm going to compute the slope and the intercept. With a random polygon, I'm not going to run into vertical lines. So if you want to be more rigorous, that case would need to be considered separately. And you see that we will divide by 0 if one of the coefficients in the second column of the equations matrix is 0. So with the slope and the intercept, so starting from the equation here, so I turn this inequality into an equality, computing the slope and the intercept, and then I'm making a range of 10 points, so 10 points that are in the interval 0, 1, and that's used to evaluate the line. So here we see the plotting of a line in matplotlib. And that corresponds to the top edge here. So we have we can do this now for one line, so we can make loops. Later I want to colors, so I imported the color map, the CM, and I'm using this jet predefined color map. I will have as many different colors as I have equations. So this Jupyter notebook contains a program, and it should work for any random polygon. So the instructions that I prepared are here written in a loop. I have in this example 5 random lines, and here you see the 5 different colors. So for every line segment I have a different color. This is important because with every line segment corresponds one vector. So the next plot that we are going to make is the vector plot. So for that I'm using Quiver. So all the vectors, I have them originate at 0, and the orientation is computed by the first two columns from our equations matrix. So here you see the plot with the corresponding colors. So we have the orange outward pointing normal that will point perpendicular to this orange line here, which corresponds to this rightmost edge. Okay, so let's now do everything in one figure. And here you see at the left, we have the representation of the convex hull as a collection of points with the lines passing through the edges. And at the right, we do have the vector representation. So the nice thing about this Jupyter notebook is that it runs as a program, so I can run all cells again, and then NumPy will generate other points. So here you see I have a different shape with 10 points. I have different lines, and I have a different vector configuration. And the code still works for this case. If you are very unlucky, then at some point you may have a vertical edge showing up. Okay, so this gives a computational introduction to the subject of working with polygons. Polygons now defined also as a finite set of half planes. In the previous lecture, I outlined an algorithm to construct the convex hull given this half plane representation. Okay, that's an introduction. This will allow us to generate as many linear programming problems as we like. So this Jupyter notebook gives some geometric intuition, but it's also useful if we want to generate test problems. Okay, linear programming. So I start in general. So what is a linear program? It has exactly nothing to do with computer programs, but programming should be seen in the planning. So we want to optimize, say we want to maximize profit subject to constraints. Constraints imposed by the available resources, and also often the constraints on the production resources, one can say labor, capital, materials, and then there might also be constraints on the certain demands that you need to satisfy. So linear programming has many applications. So there is the obvious economical application. So, but here we view this from a geometric perspective. So we have given a finite set of linear inequalities. Every linear inequality defines a half plane. So if I formulate this here in any number of variables. In practice, people can solve linear programming problems with millions of equations, millions of variables. So the geometric way of viewing this will not really scale that well because we will have an exponential number of the geometric complexity may overwhelm us. But with linear programming, if we want just one vertex that satisfies this problem here, then linear programming gets that solution faster. And it's also important for us doing polyhedral computations in any dimension. It actually always boils down to linear programming. Okay, so here is our geometric interpretation. So we want to maximize a linear everything is linear here. We have a linear functional 2x1 plus x2, and we have our constraints. The constraints are all formulated as less than or equal constraints. Why is that? Well, the vectors that we will then obtain are outward pointing vectors. So any linear program has a dual. So if you maximize profit, you minimize costs in economic terms. That's the quickest way how I can say it. Then we have inward pointing normals because our inequalities are oriented differently. So here is the picture. For every constraint, I have a black line. The green shaded area is our polygon, the polygon defined by those linear inequalities. In red is the objective. So the objective has no offset. It is a vector, 2, 1, and you can draw all the lines in that are perpendicular to that vector. And here I have drawing for every vertex. So I have 6 gone. For every vertex, I have drawn one line. Actually, I have drawn a little bit too many lines. But you can order all the vertex points, ordering corresponding to the value of the objective. So you can see that we have the two basis points, 0, 1, and 1, 0. The 1, 0 is more advantageous than the 0, 1 because its value at the objective function is 2. At the leftmost point, the value of the objective function is only 1. So if we do this in the plane, we can simply solve this by enumerating by a convex hull problem. We have all the vertices and we evaluate the objective at the um, vertex points. In some sense, that is the solution to our linear programming problem in 2 dimensions, because we know how to construct convex hulls in n log n, and we can evaluate all the vertex points. So that's a linear operation. So we can already solve linear programming in n log n time by constructing a convex hull of the feasible region. So here you see the objective and the half planes. There are the constraints and also the interpretation here. So why are we looking at outward pointing normals? Because we are maximizing. So you could also see these red lines. So the red lines starting from left to right, you kind of sweep, and you start at the leftmost and you end at the rightmost. If your coefficients of your objective function are all positive, then the rightmost point will actually be the value of your objective function. So the geometric interpretation here also of these vectors, the right-hand side is of the equations are how far you can push. So I have here shown all the lines that are perpendicular to the red normal, which represents the objective function. You could do the same for every edge. So for every edge you have an outward pointing normal, and you can essentially the edge will be how far you can push it in the direction of the outward pointing normal. So you have these half planes, and what is the limit? What is the line to which the line that you shouldn't cross, or if you cross it, you go outside your polygon. All right, now here is the problem specification now for any dimension, D again. So we are seeing a vector on input defines the objective. That's the direction where you want to go inside your polyhedron or in your polygon, polytope, if it's bounded. So we have the input specification and we have a polyhedron defined by these half planes. Now, is this a well-defined problem? Do we have a solution actually? And if we have a solution, is there a unique solution? Before we start looking at algorithms, let's first looking at the cases. So we can have a unique solution. The problem can have no solution at all, and this can be characterized by an empty polyhedron. Uh, Now, if you see a polygon defined as a convex hull of points, there is always a solution. But if you start out with linear inequalities, it's not too difficult to come with an inconsistent set of linear inequalities. Perhaps exercise 0 is what is the simplest non-trivial, so you have to have at least two half planes. What is the simplest case of infeasible problem? Simplest non-trivial one. Solution: two parallel lines, and the half planes are excluding. So in general, we have a polyhedron. So that means that our the intersection of all the half planes is not bounded. So it could be that there is no optimal, the optimal value is just infinity. So if the polyhedron is unbounded and the objective function is such that you can push your objective all the way towards infinity, then you have an unbounded solution. Uniqueness, so we will have unique, so we like uniqueness, but the solution will not unique if actually the objective vector is parallel to one of the outward pointing normals. And then actually the entire edge of the polygon is actually an equally valid solution. So the first exercise asks you to reason about the reverse. If you have a solution that is not unique, is it because you have this fact that the objective vector is parallel to an outward pointing normal? So you can start by, if you have not a unique solution, then you have at least 2 points of the same objective value. And then actually you can show that you have all the convex combinations that are also equal value. And the convex combinations, there should be an edge. And the normal to the edge is actually parallel to the coefficient vector of the objective. So that's the solution of the exercise. Certainly making a drawing, so I say otherwise make a drawing, but also in case of a proof, it's always good to start your idea in this course with a picture. And with matplotlib, we know now how to make pictures of polytopes and polygons. Okay, if we have a polyhedron, then we can always bound it by adding lower and upper bounds. So we can add constraints. It's similar when you make a drawing, we always have a viewing window. So we have the limits for x and y axis. So we have these orthogonal wedges in the dimensions that come in. And if the solution is not unique, then actually we can make it unique by convention. Always take the lexicographically smallest or the leftmost solution if we think about two dimensions, and then we have the solution. So whenever the polyhedron is not empty, we always can say that we have a unique bounded solution. By picking large enough numbers for our wedges, and also by the convention that we are picking the leftmost point. Okay, I'm halfway in here in this lecture, so we have defined the problem. Let's now look at an algorithm. So the purpose of the lectures is that you get to read the book. And now we actually transition to the approach of the book. In some sense, the convex hull problem solves our algorithm, our problem, except that we have given our problem as a tuple of half planes. And we would like to define an incremental algorithm, adding the constraints one after the other. This has advantages. You can kind of see if you have a real production problem. At some point, adding more and more constraints, at some point, you can no longer have a feasible solution. So that is also what is indicated here at the bottom line of the slides. Geometrically, it means that the regions, the feasible regions, are getting smaller and smaller. All right, so we will have an invariant. The invariant, as we are adding more and more constraints, the invariant is that we have an optimal vertex. And that optimal vertex will actually decrease in value. So we have a bounded problem because we have these wedges, M1 and M2. So initially, if the region, so we always start with a square or with a rectangle, all our variables are typically positive, and we have so the I equals 0 in this case. So we start at one of the corners. If all the coefficients in our objective are positive, we start at the right top of our rectangle. Okay, so we have two situations. So if the current optimal vertex is vi minus 1, so v negative 1 will be the topmost corner in case all the coefficients of the objective are positive. We can check very quickly whether the optimal vertex lies in the half plane defined by the new constraint. If that is the case, then we don't have to do anything. The optimal vertex of the next stage is actually the previous optimal vertex. If not, then actually we have to compute a new edge of our feasible region. So either it could be that we end up with an infeasible region, or we have a new edge, we have a new half plane that we are adding. We have two cases. So we have the case when we are adding H5. Here I'm indicating that we have four half planes. You could also see this a little bit as the bounding box, the orthogonal wedges, but assuming that we started with a square to begin with. if the fifth hyperplane is only chopping off a corner at the bottom, then the fifth optimal vertex is the fourth. Otherwise, if we add the second case, if we chop off a piece from the top, then you see that we have our optimal vertex actually changes. Also, we have only one vertex here, but it could be that we have an entire line, an entire line segment, for which we have the same value. In that case, we take again the leftmost vertex. Okay, so let's look at the correctness. So if we add a half plane and the optimal vertex lies on there, then the maximum cannot go smaller over a smaller set. So in that sense, it's just one line. In the second case, we have the line, adding a line. We have two cases here. If it's the empty set, then we are done. Assume that it's not the empty set. Then we must have that the optimal vertex lies on the line, actually lies on the line that we intersect with the polygon. Suppose that this would not be the case. Okay, suppose that we would have a point, so it's the optimal vertex would be inside the polygon. But then we can prove that if we are taking the line segment between the previous optimum and the new optimum in the interior, that actually we can find a better optimum. So actually the V6 as it is drawn here cannot be the optimal vertex. So at the left of me here, at part of the slide, we have the picture proof. The text at the right are actually the explanations. So the sentences that need to be written when you are writing your own proofs. So we are using here the linearity again. So the objective is monotone increasing. So as we move on the line segments, as the objective is linear. So that's an important observation here. We have to use all the facts, all the properties of the problem. Okay, that concluded that lemma. So let's now derive an algorithm. So we know that the new objective lies on the line. Now, how do we compute that next problem? Well, we do some algebra here. So what we can do is we can eliminate. The second variable. So we have the equation of the line from the half plane, from the input, and we eliminate, and this actually is equivalent to slicing the polytope with a line and restricting the polygon to all the points on the line. So algebraically, this gives us a one-dimensional linear problem. And we can solve this problem in time proportional to the number of inequalities. And how do we do this? Well, the sentence above the lemma says that our inequalities are very simple. So we have either an upper or we have a lower bound. So we are left with these constraints, and we have to select basically the maximum, so the lowest around allowed upper bound for x1. Okay, so now here we have our two-dimensional bounded linear programming problem that will, starting with the wedges, we have one corner of this box that bounds it. And then we're going to add more and more equations. So we have the one-dimensional problem that is solved in case that the added half plane cuts a corner from the feasible region. Okay, show the correctness. So in the correctness, you must use the previous lemmas in observing also that the cases are exclusive. So the tests in if the if test and the else test in statements 3 and 5 are are exclusive. So these are the only two cases that you have. And then also in the else case, it's broken up in two cases. Either the one-dimensional problem is infeasible. If it is infeasible, if that one-dimensional problem is infeasible, then you have to write that also the two-dimensional problem is infeasible. So there is a 1-to-1 correspondence between these two problems. And we have the lemma. So in that case, we return the first constraint that makes the feasible region empty. So on return, we either have a vertex or we have an index. In some sense, this is also an invitation to look at the book. So the slides and the lecture should be more or less self-contained, but if my explanation is still somehow not clear enough, please read the textbook at this case. Okay, I'm close to the end of my lecture here. So the cost of solving a one-dimensional problem is proportional to the number of constraints. So in particular, if the coefficient cost would be 1, we would be adding 1 plus 2 plus 3 plus 4 plus 5, and we know from this geometric sum that this is quadratic. And here you see a case where this essentially is happening. We start with two hyperplanes, H1 and H2. So this is actually one wedge here. But then all our other hyperplanes that we are adding are actually decreasing the point. So each time we actually have a new optimum. So the C, this vector here is the objective. So you see that if you want to solve linear programs in an incremental way, then you will have to tolerate or that the cost is quadratic. And this is very disappointing because we know we can construct convex hulls in n log n time. And actually, if we do it here, we have a quadratic time. So we will solve this problem in the next lecture. So in the next lecture, we will say that if we are adding our half planes in a random order, and you could also see it here. So the inputs are actually in unlucky order. If you would have the seventh half plane earlier, the lucky order would be you consider H7, H1, H2. then actually you are in the lucky case that the test is always, it will be very quick. Um, all right, I have my Jupyter notebook still up. Here it is again. So I invested some time in making it, and the benefit, other than the geometric insight, is that it allows you to generate many examples. The feasible regions are always bounded convex polygons, except if you would take only 1 or 2 points, not a trivial case. But here we can generate many linear programming problems. So what you should do, so let me read the exercise. So the first step is essentially running the Jupyter notebook. You will make a plot of the feasible region. We have the equations. So the equations were used to formulate normals. What you should do here, and you could also see this as a very simple Python programming exercise, you write down the equations of the half planes. So it's solving this exercise would essentially get the ABC out there. And the Q-Hall convention, you actually write the equations. So here you have the coefficients, and you write them, you print them out in this format. So you loop over the equations. Generate a random objective function. So we have the vertices. So you can evaluate all the vertices at this random objective function. So this will allow you to solve the problem, find the vertex for which the optimum occurs. So, and then the last exercise, the last step in this problem is to make a plot very similar to here. So when I prepared the slides for the very first time, it took a long time to get these Tixi pictures done. And here you see that the Tixi is done for a very particular case. With matplotlib, draw these red lines through all the vertices, and make a plot also like this. Okay, so this is a computational exercise extending essentially this plot here, the plot at the left. Okay, I'm at the end of this lecture. So we are in the middle of chapter 3. We are in the middle of week 4 in this semester course. We have about 40 lectures, so we have covered a great deal. Linear programming, the lecture is self-contained. From a geometric perspective, it can be solved just by the convex hull, but it's also a very good opportunity to get a little bit more familiar with the half-plane representation of a polyhedron.